In everyday conversation, we often use the word theory casually. We talk about having a theory about why our favorite team lost, or a theory about the best way to bake a cake. In these contexts, a theory is more like a hunch or a guess. It's a tentative explanation that might be based on some observation, but it's not necessarily supported by strong evidence. In the realm of science, however, a theory carries a much weightier definition. A scientific theory is not a mere guess or speculation. It's a well-substantiated explanation of some aspect of the natural world that has been repeatedly confirmed through observation and experimentation. It's a powerful tool that helps us understand the universe and our place in it. Think of it this way: if scientific ideas were a house, a fact would be a single brick. A hypothesis would be a blueprint, and a law would be the measurements and dimensions. A theory, then, is the entire house. A comprehensive framework built upon a foundation of facts, shaped by hypotheses, and adhering to laws that explains how everything fits together. So the next time you hear someone dismiss an idea as just a theory, remember that in science, a theory is the pinnacle of understanding. It's the highest level of scientific certainty we can achieve. It represents the best explanation we have, based on the available evidence, for how the natural world works. Scientific theories aren't built on shaky ground. They rest on a foundation of 6 key characteristics that set them apart from mere conjecture. First, they are well substantiated. This means they are backed by a large body of evidence from multiple independent sources. It's not enough for a theory to explain just 1 or 2 observations. It must account for a wide range of phenomena. Second, scientific theories are explanatory. They don't just describe what happens, they explain why and how it happens. They offer a coherent framework for understanding the underlying mechanisms and processes at work. Third, theories are testable. Their predictions can be verified or refuted through further observation and experimentation. A good scientific theory makes specific, falsifiable predictions that can be put to the test. Fourth, and closely related to testability, is falsifiability. A scientific theory must be open to the possibility of being proven wrong. If there's no conceivable observation or experiment that could disprove it, then it's not truly scientific. Fifth, scientific theories tend to be broad in scope. They often encompass a wide range of phenomena and can be applied to different contexts. They provide a unifying framework for understanding seemingly disparate observations. Finally, scientific theories are predictive. They allow us to make predictions about what we might observe in the future, or in situations that haven't yet been studied. These predictions can then be tested, further refining and strengthening the theory. To fully appreciate the significance of scientific theories, it's helpful to distinguish them from other terms often used in scientific discourse: hypotheses, laws, and facts. A hypothesis is a tentative explanation for a specific observation or phenomenon. It's a starting point for investigation, an educated guess that can be tested through experimentation. For example, you might hypothesize that plants need sunlight to grow. A law, on the other hand, is a statement that describes an observed regularity in nature. It tells us what happens under certain conditions but doesn't necessarily explain why. Newton's law of universal gravitation, for instance, describes the force of attraction between objects with mass, but doesn't explain the underlying cause of gravity. A fact is a statement that is accepted as being true based on current evidence. Facts are often directly observable, like the fact that the Earth revolves around the Sun. However, it's important to remember that scientific facts are always open to revision as new evidence emerges. Theories, as we've discussed, are comprehensive explanations built upon a foundation of facts, shaped by hypotheses, and often incorporating laws. They provide a broader framework for understanding the natural world. For instance, the theory of plate tectonics explains the movement of Earth's continents, a phenomenon described by numerous geological laws and supported by countless observations. Section 4. Titans of Scientific Thought. The history of science is replete with groundbreaking theories that have revolutionized our understanding of the universe and ourselves. Let's delve into a few iconic examples. Darwin's theory of evolution by natural selection. This cornerstone of biology explains the diversity of life on Earth as a result of gradual changes over millions of years, driven by the process of natural selection. This theory profoundly influences our understanding of genetics, medicine, and ecology. Germ theory of disease. This theory, pioneered by Louis Pasteur and Robert Koch, revolutionized medicine by establishing that many diseases are caused by microorganisms like bacteria and viruses. This understanding led to significant advancements in sanitation, hygiene, and the development of vaccines and antibiotics. Einstein's theory of general relativity. This groundbreaking theory redefined our understanding of gravity by proposing that it's not a force acting at a distance but rather a curvature in the fabric of space-time caused by mass and energy. It has profound implications for our understanding of the universe's evolution, black holes, and the nature of time itself. The Big Bang Theory. This cosmological model describes the universe's origin from an extremely hot, dense state roughly 13.8 billion years ago. It's supported by a wealth of observational evidence, including the cosmic microwave background radiation and the redshift of distant galaxies. Quantum theory. This revolutionary framework governs the behavior of matter and energy at the atomic and subatomic levels. It has led to the development of countless technologies, including lasers, transistors, and nuclear energy, and continues to push the boundaries of our understanding of the fundamental nature of reality. Section 5. The enduring power of theories. Scientific theories are not static pronouncements, they are dynamic, evolving frameworks that are constantly refined and expanded as new evidence emerges and our understanding deepens. They are the engines of scientific progress, driving innovation, shaping our worldview, and enabling us to make sense of the universe we inhabit. When we embrace scientific theories, we embrace a way of thinking that values evidence, logic, and critical analysis. We acknowledge the provisional nature of knowledge, always open to revising our understanding in light of new information. The next time you encounter a scientific theory, don't shy away from its complexity or dismiss it as just a theory. Instead, embrace the opportunity to delve into the fascinating world of scientific inquiry. Explore the evidence, grapple with the concepts, and marvel at the elegance and explanatory power of these remarkable constructs. For in the grand tapestry of human knowledge, scientific theories stand as our most profound and awe-inspiring achievements.